Thank you. Good evening, everyone. My name is Megan Neer, and I am pleased to welcome you to the Community Science and Technology Virtual Seminar Series sponsored by Pacific Northwest National Laboratory. This seminar series is intended to introduce you to the world-class research that has been taking place right here in your community. It is normally held in person, but given the current unfortunate COVID-19 situation, we modified the format and hope you enjoy the virtual seminar. We expect to continue into the foreseeable future and have seminars scheduled through June as of right now. More information and registration for webinars can be found on the PNNL events page at pnnl.gov/events, which is in the chat window. And we'll be sure to promote some of our upcoming talks at the end of tonight's presentation. Now I'd like to pause for a moment and do a quick poll. If you could turn your attention to the screen. Our first poll is, where are you joining us from? And it looks like we have the majority of folks joining us from the Tri-Cities and surrounding regions tonight. Thank you all for joining us wherever you are joining us tonight. And then we also were hoping to find out what best describes the stage of your career. Are you a student? Are you in your career still? Are you retired? And it looks like we have a nice mix tonight from students all the way to retired. So thank you for that. We appreciate your feedback. So at the end of tonight's talk, it would be great if you could take our brief survey, and the link has been put in the chat window. It's also shown here on the main screen. For your convenience, we'll display and share the link again at the end of tonight's talk. We really appreciate you taking time to give us this feedback. We want to make sure that you see value in these seminars, and we'll make improvements based on your feedback. This is also your opportunity to sign up to receive emails from us about upcoming seminars, including the special series like the one we did on COVID this past March. If you're interested in viewing recordings of any of our previous presentations, please go to pnnl.gov/events/past, which is also in your chat window. Now, before you learn more about tonight's topic, your presenter is going to give you a brief overview of the National Laboratory System and PNNL's missions. You will also learn more about Battelle, the operator of PNNL and the Tri-Cities' largest employer, and its staff, and how they take pride in being excellent community stewards through philanthropy and volunteering. Now let me go ahead and introduce you to tonight's speaker so we can get started. Tonight's presentation is Building Beyond Lithium Batteries, from Human Intuition to Artificial Intelligence. Your presenter is Vijay Murugesan. Vijay is a physicist and leads a team that conducts testing and development of advanced energy materials at PNNL. His research focuses on predicting charge transfer and storage mechanisms in electrochemical materials. Vijay holds a PhD in physics. Welcome, Vijay.
Thank you, Megan. Can you guys hear me?
We can.
Yes, thank you. Thank you for this great opportunity. It's a pleasure and an honor to introduce our research to the broader community. But what we are going to talk about today is going to be going back from the history of the battery and all the way to the future of the battery. So, like Megan said, let's start from, okay, slides. Slide is not advancing for some reason. Okay, we have to do it this way. So PNNL is one of the 17 national laboratory funded by Department of Energy, US Department of Energy. So it's on the Pacific Northwest, and PNNL is a short for the Pacific Northwest National Laboratories. PNNL is focused on DOE's mission area. Our main goal is to meet the national needs. It could be vary from scientific discovery to ensure energy independence of the US government, national security, and also the environmental management. So we work on wide variety of areas on the topics. PNNL is a huge economic engine. We have almost 5,000 employees with an annual budget of more than $1 billion. The last year alone, we had 340 inventions reported and then 81 patents totally awarded. And we also granted 36 licenses, meaning that the invention from PNNL has been licensed for commercial productions and that. We also have generated more than 1 billion economic output, and it also generated more than 7,000 jobs in the community and around. So PNNL is very take pride in helping and philanthropic works with Petal. So last year alone, we did more than $1 million philanthropic investment, and also the staff, PNNL staffs, are actively involved in the local community organizations and also the team battle volunteer hours also. With that, let's get into the research topic that we are going to talk about. When you think of battery, at least for the modern battery, you will immediately think about lithium, right? Let's start from there, and then we will see how that the lithium battery was being built, and then how the future looks like. Lithium has been discovered actually in 200 years ago. So in 1817, lithium, the first discovery was made about lithium. It was an alkaline material. The good thing, interesting thing about lithium is that it's a first metallic element that's in the periodic table. So with atomic number 3, this is the lightest metal, and also it is one of the interesting and highly reactive metal. It took about 100 years almost to understand the electrochemical property of lithium. For example, that lithium holds 3 electrons, and then 1 electron can be removed, making it lithium as a positive cation, and that can be reversed back. So that kind of electrochemical phenomena, it took about 100 years for us to do it. So one thing that we need to highlight here is that lithium is extremely reactive metal. So having a pure lithium metal is almost a challenging aspect. So in the picture down here, you can see that lithium needs to be stored in a highly inert atmosphere, preferably in an inert gas atmosphere. So there are some technical challenges in handling this material, but it also gives a huge potential in terms of electrochemistry. So when you think about the battery, we will introduce what is the first battery, or the battery based on the electrochemistry at least. The electrochemical battery, first one was Daniel cell. It was using zinc and copper. So it was actually first demonstrated in 1836. Then it took about 155 years to develop the commercial lithium battery. So the first electrochemistry, where you take the chemistry and then you produce electricity, or you take apply the electricity and change the chemistry. So both can happen in electrochemistry, and then that it took 155 years to develop that concept into a commercially viable lithium-ion battery. So the lithium-ion battery that you normally use in your cell phone or laptop is typically based on a lithium-ion battery, where you have a graphite on one side and then lithium cobalt oxide on the other side, and then lithium basically shuttle back and forth. This invention has changed the human life so much, and to appreciate and recognize that 2019 Nobel Prize was awarded to the inventors of the lithium battery, Stanley Whittingham and George Goodenough and Professor Akira. So with this battery that changed the world, now we are looking forward and see how we can capitalize on this technological advancement and then move beyond this. So as I said before, it's about 200 years ago, the first lithium was isolated and discovered. And then it took about almost 200 years for us to come to the stage of using the lithium metal based batteries into this. It changed the human life, right? If you can remember the telephone systems in about 50, 60 years ago, and then now you can imagine the telephone now, the mobile phones. So all these revolutions are the fundamentally because of lithium-ion batteries. So the question is that we achieved so much over the years, but what is the next one? So what is the next revolution? So what can we do from standing from here and then looking ahead, where we can go? That's what this talk is mostly about. So if you look at that, where we are now, lithium-ion batteries were uh, basically being produced and commercialized for consumer electronics. So if you look at here, the blue line here, in the last 10 years, that started changing. So 10 years ago, around 2010, more than 90% of the lithium battery that produced were actually meant for commercial applications. Sorry, the electronic application, commercial electronic applications, right? But in the last couple of years, the requirement from the transportation industry has overgrown the consumer electronics. The transportation industry, by which I mean that hybrid vehicles, plug-in vehicles, electrical car, and those type of applications that started overgrown. So lithium batteries start filling in those gaps as well. And recently, there's one more candidate, the player that comes into is the large-scale energy storage. So the large scale energy storage is about, you don't need to move the batteries. You can install the battery, but it can power the entire city, or it can stabilize, load stabilize the electrical grid. So it has a much bigger and different applications. So going forward, we will be discussing two type of batteries that need for the two type of batteries. One is about the transportation batteries, the battery for the transportation application. The second one is the battery for the electrical grid applications. Because if you look into the future predictions, the battery that required for transportation is going to be way more than the consumer electronics. I think. In fact, the large scale energy storage aspect is also going to be larger than the consumer electronics. So this is all going to happen in the next 10 years. So we need to act very fast so that we can meet the demand for the future. So when we're trying to think about making a new battery or developing a new system, we need to think about few aspects. So one is that what is the raw materials? Where does it come from? Can we make sure that there is enough supply of the raw materials? The second one is that what type of battery we are going to make, because that will depend on what is the application. As I said, right now we are talking about two different applications. One is for the transportation application. The second one is for the large scale grid level storage application. So the bottom examples, like I said, you can power the truck or even a bus, a car. Those transportation application has a different demand. For example, the battery that you want to power that needs to be small and lightweight, and also has to hold a lot of power on it. And on the other hand, that the stationary application, it is a different type of demand. We don't worry about too much about the size of the battery, because most often these will be installed in some remote place on the ground. So weight is not a problem, but the long-term cycle life is a problem. So your cell phone battery or your laptop battery, for example, they last about 3 to 5 years, right? The car batteries are typically 5 to 7, 8 years. That's what the goal is. But the large scale, the grid level application batteries are expected to stay more than 10 years, preferably 20 years or more. What that means is that you should be able to discharge the battery more than 10,000 times without any significant capacity loss. Basically, there is no degradation for at least 10,000 cycles. That's when we can apply for the large scale application. So as you can see that each application demands different type of battery. So obviously we need to make a different type of materials and then make it a different type of battery that's specifically designed for the application. So what is the DOE's goal here? So recently Department of Energy put out a big a roadmap called the Grid Scale Energy Roadmap. Energy Storage Grand Challenge Roadmap, which it has basically 3 aspects into it. One is that innovate here, make here, and deploy everywhere. So innovate here means that basically we need to come up with a new materials, new type of molecules, new type of electrolytes, new type of components. We need to come up with those, and then we should be able to make it here, meaning that, as I said before, the supply chain and the industrial infrastructure, everything needs to be in place so that we can innovate and make here in the United States and then deploy everywhere. On that, the Department of Energy has come up with a plan. The plan is that As I said, that DOE has more than 17 national labs. PNNL is one of that. So they identified PNNL is the lab for the material to devices. So basically, most of the innovation will be happening here. For example, the next level, that device to system level, which is connected to the innovation and also the making part, and that will be hosted by the Sandia. And then the system integration and then deployment, that level will be hosted in Oak Ridge and so on. So each lab has been identified to lead particular task, and PNNL has been identified to lead a task about innovation part. So that's why DOE is establishing a new facility called the Grid Storage Launchpad here in PNNL to make the innovation faster. So. Okay, so lithium, if you look at the lithium batteries, the beyond lithium battery field, it's so huge. There's so many different type of material that could potentially replace lithium. The problem is that identifying the proper material and then be able to predict and then use it. One of the main challenges in terms of looking beyond lithium is that not finding the material or atom, but it also about putting two materials together and predict how that will react to each other, right? When you look at the battery consists of three main components, right? Anode, cathode, and then there's an electrolyte. So the reaction between the anode and the electrolyte has to be stable, and then the electrolyte versus cathode needs to be stable. All these chemistries need to be fine-tuned so that you will have a viable and realistic battery. So the scientists, we are so far, we are able to predict the property of a material, but what we are lacking is that our ability to predict the material property when it's exposed to a different material or a different type of electric field and things like that. So that's when the challenges comes in. So that's what we need to do. So there is a huge level of fundamental science needs to be done so that we can move beyond the lithium battery. So scientists already identified few elements on that. For example, sodium could be one of that, magnesium, aluminum, zinc, all these elements they identified that could potentially replace lithium and make the battery more useful. For example, if you take the magnesium, it has a lower gravimetric energy density, meaning that the battery may weigh little higher than lithium battery, but it can hold more energy in terms of the volume. So that magnesium, that's because that magnesium is 2 plus. So unlike lithium, which is can only share one electron with the under electrochemical conditions, magnesium, on the other hand, can share two electrons. So it's a twice the bank for the same power, right? So we identified certain type of atoms, and we are going in a fundamental level to understand how to make use of these unique atoms to serve as a next lithium ion. So for that, DOE, the basic energy science of DOE, established a huge program called the Joint Center for Energy Storage Research, or in short, JCSER. It is the research center based on 6 national labs, and then 11 universities all partnered up together to come and understand what can be done beyond the lithium battery. So like I said, magnesium, zinc, aluminum, sodium. So what can we move beyond the lithium ion batteries, and what type of material needs to be studied, and what type of reaction needs to be predicted and understood so that we can make the next level of battery. So this is a huge program under BES. PNNL is a part of it, and it's led by Argonne National Laboratory in Chicago, and Berkeley and Sandia are all part of it. So this is a huge effort towards the fundamental science of the battery, especially looking beyond the lithium battery. So what is the goal of the JCSER? So the idea is behind that is that can we put together atoms and molecules from bottom up? Can we design a molecule and materials so that will serve on the next level generation battery? So for example, if you want to make a magnesium battery, what type of materials like electrode and electrolyte needs to be built? So what are the challenges in building those type of materials to make the battery working? So what type of challenges in terms of viability, predictability, and then reliability will come in? What type of reaction we need to be predicted so that we can make a reliable battery on that. So those are the concept. So basically a bottom-up assembly of a material based batteries for the next generation. So that's what this project is about. So what's PNNL is doing in this big project? So PNNL's role is to do the in situ measurements. So basically the PNNL build some unique tools that enable us to look inside the battery when you have a charge discharge process. So for example, we build NMR, XPS and TEM. So NMR is a nuclear magnetic resonance based spectroscopy. XPS is X-ray photoelectron spectroscopy, and TEM is an electron microscope. So what we build is that very unique. It's not commercially available instrument. This is specifically built to look inside the battery when you are discharging it. So we make new materials, new battery, then we will put it together, then we will charge the battery, and we will see how it performs, how it degrades and things. The uniqueness about this is that people try to make one instrument for the battery, for example, Institute NMR or maybe Institute TEM, but nobody has built the suite of spectroscopic capability that can go after the challenges of the materials in the lithium battery or any battery for that matter. So that's why PNNL is very unique, and that's one of the reasons that PNNL is being selected to be innovative for materials for battery. So with that, as I said, the Joint Center for Energy Storage Research, the Fundamental Science Project is already working on this. One of our main target is to make a magnesium-based battery. Like I said, magnesium is 2+, meaning that each atom will share 2 electrons rather than 1 electron, so twice the bank. But the challenge is that to move the 2+ ion across the back and forth is going to be challenging. So there needs to be new materials needs to be developed and new electrolyte need to be developed. So we are using a computationally driven project called Materials Project, which goes and identify what type of material that can be used so to insert the magnesium inside into it, and what type of material that can conduct the magnesium, basically transport the magnesium back and forth. And we are doing that through the electrolyte genome project. So this is an ongoing work. It's a very recent work. Um, we are in a stage that we are still not yet ready to release some of the material that we are looking into it. But the initial results are very promising, and we got some fantastic results. So that I'm hoping that we will be able to move the field much further faster and develop these batteries in soon. With that, I'm going to change the gears, and I'm going after the grid scale energy storage I talked about. So these are the batteries that you need for grid level stabilization. For example, in the daytime, the electricity production the usage of electricity is very high, and then the nighttime, the electricity usage is very low. But the electricity that's produced during the nighttime, that excess electricity, can be stored into the energy storage, the batteries, and then it can be used. So that way we can able to stabilize the electrical grid. So it will be a reliable and resilient electrical grid. So that is one of the main goal of the Office of Electricity under DOE. So Office of Electricity in DOE has given a big project to PNNL to develop these type of batteries. So the goal is to develop really commercially viable, safe, and large-scale batteries that can go beyond 10,000 cycles and work more than 10 years. So that's our goal, and this is a project on that. The reason why we can't use lithium battery for that is because obviously of the safety reason. Very recently, people tried to install the lithium-based battery for large-scale applications, but very recently there was a big fire. There was an accident in Arizona where they were trying to use a lithium ion battery for a large scale application. So now you can imagine when a cell phone explodes, you see how much trouble it can cause. When a laptop explodes, and the car explosion because of the battery fire. Now imagine that thousands of batteries that stack together in a tight place, and you're charging and discharging in unrealistic ways of so that much of energy that's stored in the lithium battery is a potential for a catastrophe. Unfortunately, it recently happened in Arizona. So that's where 8 firefighters get hospitalized because of that fire. So all these incidents are pushing us more and more towards a safer, cheaper, and cleaner batteries toward that. So that's where the redox flow batteries are coming into the play. So redox flow batteries are operating in a completely different mechanism than the regular lithium ion battery that we discussed before, right? Or even the magnesium batteries. So the redox flow batteries typically have two separate tanks, and the two tanks will be filled with the electrolyte, and then you can pump it through the electrode. So instead of keeping everything inside the battery, you basically separated the stored chemical apart so that it become more versatile. What this means is that you don't need to charge the battery where you want to use it. Basically, you can charge the liquid somewhere else, and then you can bring it here, and then you can fill it up, and then you can run the battery. Like you fill the gas tank, the same process, you can also do that. But you can also charge it on the same spot. So it gives you more versatility, and also the bigger the size of the battery, the energy can be stored. It's basically how big the tank you can build, right? So that's also been a very helpful thing. And if you combine that with that, if the electrolyte is water-based, imagine that it's a simply water-based electrolyte, then that cuts off all the safety problems and associated cost issues, and things will be much cheaper, right? So that's what we are planned to do. That was we are doing during the Office of Electricity project. So just this is a brief slide that what we did. I will go in explain two of this, the mixed acid system right here, and then the organic flow on this. But just to give you an overview, PNNL developed 4 different new kind of electrolytes that's already been reportedly much better than the theoretically predicted electrolyte performances. So one of the main reason is that we are able to understand at atomic level what happens and why it is doing that type of reactions. We are able to predict many reactions and so on. So for this talk, I'm going to talk about the mixed acid system right here, and also the organic flow battery that right here. So when we got the project and when we've been asked to design a new electrolyte for the redox flow batteries, we looked into this and said, okay, how are we going to make a new electrolyte that's going to be water-based? It's going to be extremely safe and also cheap and also highly reliable, meaning that it will not make any unwanted reactions. So those are our main requirements. And then when we look into the material aspect of it, we said, okay, we need to understand what is the redox potential, basically how much energy you need to spend to make it work. And what is the solubility, basically how much material that you can put inside the water before it starts precipitating out. And then the stability. So that means that how can we operate in a wide temperature range? So if I make a battery, it should work in Alaska as well as in Texas. It should work with the same performance level without any trouble. So all these factors are very important when we design. So that's when the challenge comes in. You need to make a material that is available, safe, and also meet all these criteria. So before we get into the project, the vanadium battery project has actually been tried by many people, including NASA, to as part of the Apollo mission. They want to put the one battery right up in moon so that they can use it over there whenever they visit the moon. But the problem was that the vanadium is unstable in high temperatures and low temperatures. So when I say high temperature, even a 40 degrees Celsius, about 100 degrees Fahrenheit, that you already start precipitating out things. So it start clogging the pipe and the battery fails. So when we took the project 10 years ago, that was the status of the vanadium battery project. So people almost give up on that, and they said that this is not going to work. So when we come in the PNNL team, when we try to work that, let's first understand what the problem, why it fails, and what is the challenges here. So when we try to understand at atomic level, and we figured out that the vanadium is 5 plus, basically it really lacks 5 electron. It would like to get back this electron. It attacks the water molecule and try to steal the electron from the water molecule. When that happened, the water start giving up the proton away, and that creates the reactivity chain reaction, and then it makes that unprecipitate as a powder particle. So when we understand that, we said, okay, we need to somehow satisfy the vanadium to not to touch the electron from the vanadium, from the water, but we need to give other electron source. So we decided to introduce chlorine into this, because the chlorine is nicely known to bond with vanadium and also like to share the electron. So when we did that, the precipitation stopped. The stability of the electrolyte is increased, and the overall performance of the battery also increased. So what happened is that in 2010, we took the project, and within a couple of years, we were able to understand and then modify the electrolyte, and then that we were able to test and demonstrate in a kilowatt scale level, and then it commercialized. And then 2014, the company Energy Technologies, they commercialized, and this is Jay Inslee, the governor, opening the facility and giving that. Not only Energy, there are two more companies also licensed the electrolyte, and they are now selling it and up to 1 megawatt scale batteries, I think. So this is a nice example of understanding at the fundamental science level, and then modifying the molecules, how we can make it more happen. So I just want to tie it back to remember that it took years and years for lithium battery to develop on this, but now it only takes about 5 to 6 years for us to do this, because the fundamental science knowledge developed during all these years were readily available. So we can tap into that so that we can design new molecules. So what this means is that next new battery, we don't need to wait 200 years. Because of the fundamental knowledge developed, we may be able to achieve faster. When we developed the vanadium new type of electrolyte, it became commercialized, everything was fantastic, but there was a problem. The problem comes from the cost. The vanadium is the limited availability, and the cost of the vanadium is controlled by the market. Basically, it's stock market based. So when the vanadium redox flow comes in, obviously the demand goes up, the cost goes up. So that changes the total cost of the battery. So we were struggling on that aspect. So we said, what can we do about this? So that's when we started thinking about the organic molecules. Organic molecules are carbon hydrogen based molecules. You can basically make yourself. You don't need to depend on the uh, mining from the earth or anything. We can build these molecules from the lab using the known organic chemistry. So we thought that maybe we need to replace the vanadium with the other carbon-based molecules, so that we know how to make it, and we have ability to tune the molecules. It will be easier for us to control the price and also the property of the molecule. With that, we decided to go ahead and need to try that. As we started with that, we were looking at so many different molecules, and then this is where the human intuition comes in. One of my colleague, great chemist, Aaron, he came up with a molecule, said that, okay, phenazine could be an excellent molecule because it can hold 2 electrons and share 2 electrons, and it can be stable in water-based systems. So this can be done. So we said, okay, looks very promising. Can we take this and we apply it? So we took the molecule and then we tried to dissolve it in water, but solubility is very low. It's not dissolving. So and then we said, okay, can we change the molecule? We can edit the molecule so that it make it dissolve in the water. So then we can make a battery. So we tried different type of editing. So that's where the computation comes in. The density functional theory based calculation comes in, and then the computers predicted a total of 10 different molecules that could potentially dissolve very well and also perform very well in the battery conditions. So we tested these 10 different molecules based on the computer predicted values. And then we identified 2 of them could be very potential. And then we finally end up with using one of that. So the story here is that the human intuition lead to identification of one particular set of molecule, and then it took a couple of years for us to use the computer to predict how to tune this molecule, and then a couple of years for it to finally test it and in a battery, and then in a bigger scale battery and prototyping level. But when we think about that, we said, okay, it took us about 3 years to once we know the molecule, it takes about 3 years to tune it. But we only tested 10 molecules so far. The phenazine itself has more than 6,000 variety of it. If I need to go and test each one of them, it will take years and decades of work, right? How can we are going to do it? So even more astoundingly, that the total known space of the organic molecules, the carbon hydrogen based bonding based molecules, is more than 160 billion molecules available there. So that's more than total number of stars in our galaxy and universe. So if you think about that, there could be so many different type of molecules that can potentially be used in the battery. But how are we going to identify those things? How are we going to test those molecules? So that's when we said this is not possible for humans. We need an artificial intelligence based computation to do that. So PNNL recently launched a new program called the Energy Storage Materials Initiative. So the idea of the material is that how to accelerate the discovery of the material so that we can enable the redox flow battery operations. So this is based on 3 principles. One is that use artificial intelligence to predict the molecule, and then use automation, robotic based one, to test the prediction, and then use it in the battery, make a real battery, and then validate in the real condition. So that's our goal. So with this initiative that we started with our mission as that, we started working on that. The first challenge on this aspect is that how can we teach the computer the chemistry, right? It is so hard to teach the computer the full chemistry of it, because computers only speak 0, 1, and we need to somehow have to teach the electronic orbitals. We need to understand about the covalent bonding versus ionic bonding, with the electron density. All these things needs to be done. So that's our big first challenge. So what we decided is that we will work with the computational algorithm experts to make sure that each molecule can be represented in mathematical way so that the computer can start learning from that. So that's what we decided to do that. Now we are in the stage that if we give a molecule, if you give the name of the molecule, the computer can easily recognize, and then it can build the structure for it. And then it can also predict the property, like how soluble this molecule is going to be, or how stable this molecule is going to be, and things like that. So it's an ongoing process, but as I said, it's a big challenge to teach the chemistry to the computer, but the initial success are very encouraging on that. So one of the things is that to teach the chemistry to the computer, we need a lot of reading material, right? We need a lot of data points so that the computer can learn from that. So that's where when we said, okay, we means PNNL, we don't have all the data that is needed to teach that. So what can we do is that we will use the artificial intelligence to go and learn itself from the internet. So basically any open source, it can go and read all the research articles, and then it can start learning more and more about it. So it's called natural language processing. It's been widely used by Facebook, Google, and all the social medias. So we adopted that, and then we said, okay, let's make the artificial intelligence, the computer-based system, to go and read research articles, and then it understand from that, so that it will become a part of the learning process. So we were able to do that, and now it can go and read different articles and then collect the important relevant information from that, and then it learns from that. So with that, we are able to generate a database. The database idea is to enough material to teach the computer so that it can predict, make a better prediction. So that's what we are going after. So make an enough reliable, high fidelity database with quantifiable error so that the computer can learn and then it can predict into the new materials. So that's the first part. The second part is, as I said, is to automated validation, right? So the testing of the material. So once the computer predict a new molecule or new material, we need to test it, right? In the beginning, the computer start predicting hundreds of molecules, right? And we need to test it, and it's impossible for us human to go and test everything. So that's where the robots comes in. So PNNL recently installed these 2 robotic systems. These robots can prepare electrolyte, it can prepare material, it can test the property of the materials, and then it will provide feedback to the computer. So basically, if a computer says you can prepare this and test this and this materials, then the robot can prepare those materials and then will provide the feedback to the computer. So you can teach the computer, no, you are wrong. I tested this 100, but only 10 works. Then, so the computer learn from that mistake, and then it next time it try to predict better, and it's a loop. It can go on. Obviously, it's not fully automated at this point. There's a human intervention. As I said, human intuition is a critical part of it. For example, there is still what type of molecules and what type of things that we need to focus on. There is still a human intuition that's placed into it. For example, one of the human intuition based one is to understand from the nature. For example, if you look at the biochemistry or biologically based plant system, it produces so many different nice organic molecules with high precision, high stability, with excellent efficiency also. So now what we are trying to understand is that, can we learn from that? Can we learn from plants and trees how it makes molecules? And then can we take that learning and then teach the chemistry to the computer so that the computer can mimic the same type of molecules and produce a molecule that is suitable for the battery, and that can be tested quickly using the automated robotic system, and then develop a new type of battery. So that's where we are going. That's a futuristic view of our plan. And we specifically focusing more and more on biological material because of its environmental friendliness, and also that the efficiency that the plants make these molecules. With that, I just want to give a final message, a take-home message, so to speak, is that the electrical energy storage field is completely evolving. Lithium is not the only show in the town. There is other materials and other potential compounds that are coming up. So that is because to meet the demands. The demand is changing. The demand is now it was simply powering the laptop and your cell phone. Now we need to power the car, truck, even an aeroplane. And we also need to use the battery for the electricity production and storage and entire city level electricity. So when the demand changes, the production on the new chemistry needs to also be changed. So that's where we are moving away from lithium and we are going here. So this periodic table that's shown here has shown some of the potential candidates that could produce a better battery on this. So there's more research work going on there. If you are interested in, please contact me. I'll be very happy to discuss with you on this topic. And with that, thank you very much. And I will be very happy to answer any question that if you have any.
Well, thank you, Vijay. We appreciate you taking time today to share your research with us. We have about 30 people joining us tonight, and we do have a couple of questions. So let's go ahead and get started. Okay. What about lead acid, or in other words, car batteries? Can we use that instead of lithium batteries?
Oh, okay. Lead acid batteries do not have an energy density that could come like lithium battery. So lead is a very heavy atom, heavy element compared to lithium, and also it cannot pack the same level of energy in any given volume or the weight. So for example, 1 pound of lithium battery can hold way more energy than 1 pound of lead acid battery. So that's the reason that we cannot use the age-old lead acid battery for everything else.
Okay, thank you. And are there any other atoms like vanadium that can make better flow batteries?
Yes, the iron and chromium are the two possible other contenders that could make it. PNNL is also doing a lot of work on that. Zinc is another potential atom that could be very helpful. Um, but vanadium, the beauty of the vanadium is that it can exist on 4 different oxidation states stably. Basically, it can be 2+, 3+, 4+, and 5+. That gives you the versatility to make the battery easier. But other atoms can do only 1 or 2 oxidation states.
Great, thank you. And how long would it take to identify molecules that are promising enough to be investigated in your laboratory with the computer?
It it could take at least few years because, as I said, teaching the chemistry to the computer itself is a big challenge. Um, for example, I tell you one challenge for us is that teaching the isomer to the computer. So isomer is the same uh, molecular weight and same number of atoms, same everything, but slightly structurally different, right? So teaching that is a very challenging part to that. So once you are able to do all these things, we expect that it can produce the molecules very quickly after that. But as I said, the challenge is to teach them. So I would predict a couple of years at least.
Thank you. And when you test a candidate for a cell, what do you test for? Electrochemical potential, charge rate, discharge rate, etc. And how do you test for degradation over a number of cycles?
Excellent question. So our goal is to get the solubility, whether it can be dissolved in water or other solvent. The second one is that we will check the stability. The stability means that we will check the thermal stability first. So basically, is the bond are all strong? Is it easy to break any bonds? And then we will check the electrochemical stability. Basically, we will insert 2 electron or 1 electron into the molecule and see now how the bond behaves, what is the bond strength of it. So that will help us to understand what will be the energy density of the battery and what is the thermal stability of the battery and what will be the electrochemical stability of the battery.
Thank you. And what do you find are the biggest stumbling blocks in the way of widespread deployment of electrochemical energy storage to back up solar and wind energy?
Um, as I said, this is all we're talking about stationary energy storage applications. So lithium batteries are not going to be the only thing that can help here. So we need to come up with a different type of battery because of the cost and safety that I discussed. So vanadium battery that I showed you could be one potential candidate, but that's still like the vanadium cost and things. So coming up with an optimized battery that can, for this particular application, and you need to identify a perfect chemistry for that. That would be the main challenge.
And then regarding lithium batteries, are they renewable or recyclable?
So there are some recent works about renewable and recyclable. The best battery for recyclable is actually lead acid batteries. Because every 100 battery come out of the industry, 99 of them get backs and get recycled. Lithium batteries are barely few percentage of them get recycled, but it's picking up because, as I said, the supply line of lithium and the cobalt is getting high demand. So there is a cost associated with that. So the cost justifies the need, and sorry, the need justifies the cost. Anyway, they start recycling, but it is not as good as the lead acid batteries.
Sorry, my cursor disappeared for a second. How does the USA differ or development compare to others? How does the USA's development of these batteries compare to others?
Well, in terms of innovation, US is the leader in terms of innovation. China is catching up, obviously, but the level of innovation we are talking about, looking beyond lithium batteries and making a new materials and those type of innovations are right here in US. So I would say the leader in the field.
Great. And are there other spin-offs of your research, or in other words, new machine learning techniques?
Yes, I'm not sure I can discuss all those things here, but yeah.
Understood. And so if we have one last question. Can a computer design new material or just explore the existing materials only?
Building a new material is our ultimate goal. It will be my dream project. But right now, if we give 10,000 molecules, then computer can down select to maybe 10 or 20, so that we means a human can go and test it. That itself is a big achievement, because that reduces the chemical space, parameter space for us. But I don't know, maybe 10 years from now, or maybe sooner, the computer can say that, you know what, I will build a material for you. I will build a molecule for you. That will be an awesome.
Well, thank you, Vijay. I appreciate you taking your time out today to share your research with us. And thank you to all of you for attending, taking time out of your busy schedules to attend tonight's seminar. I just wanted to reiterate, if you could please go out and fill out the survey and let us know what we did well, what you enjoyed, what we could improve upon. And I think we also have an option to share your thoughts on additional topics that you'd like to hear about. And I'd also like to remind everyone about upcoming seminars. And on that survey, you can also sign up to receive notifications about those future seminars if you didn't already do that in your Zoom registration. So on April 27th at 5 o'clock, we have Bojana Genovska talking about catalysis, and the link to her talk is in the chat window. Then we have Alicia Emerson talking about marine sciences, taking place in the Swim Bay area on May 11th at 5 o'clock. Link is in the chat window. And Lily Hale, it will be talking about chemical upcycling of plastic waste on June 8th at 5 o'clock p.m. So again, thank you to everyone who joined us tonight, and we will see you on April 27th. Have a great evening.